All right, so we are going to go, these are our second set of notes to go along with our acids and bases unit. So I just want to do a quick review of what we did in our last set of notes. And so right now I have your reference tables open, and this is reference table I and J. So let's talk a little bit about what do acids and bases have to do with reference table I and J. So on reference table I, at the bottom of this set of reference tables, and let's just make this a little bigger so it makes it a little bit better for my handwriting, we have our acid and our base neutralization reaction. So where we have the H plus is the acid. So I'm just going to draw a line down here. So then that is our Arrhenius definition. All right, so then that is a Arrhenius. I'm going to erase because I need to make this a little bit bigger, and let's go like this. Okay, so our Arrhenius definition. So Arrhenius, Arrhenius, that's two dots. So that's our Arrhenius acid, which has the H plus as the only positive ion in solution. And then our OH minus, which indicates our base, is our Arrhenius base, where we have the OH minus, the hydroxide, as the only negative ion in solution. And we're just going to scroll down over here, and then electrolytes, right? Electrolytes give you acids, bases, and salts, right? Are electrolytes because they split into their ions in the presence of water. And so those ions now allow an electric current to flow because they have mobile ions, right? An electrolyte, acids, bases, and salts. Remember, salt is an ionic compound. So an acid and a base, right, will neutralize each other. Oops, let's just get rid of that little, and make a neutral solution. So we have water, right? Water is a pH is equal to 7, which is neutral. That means that the H plus equals the OH minus, right? H2O. And then our acids have a pH of less than 7, and our bases have a pH of greater than 7, from 0 to 14. So now let's go to our next set of reference tables, our table K and our table L. So table K, we have our common acids. And again, this is going to be the Arrhenius theory of acids, where you have the H plus as the only positive ion in solution, right? Because the Cl minus would be the negative over here. Negative. And then with our nitrous acid and our nitric acid, right, we have the H plus with the negative nitrates. And then we have our organic acids down here. And then we have our COOH, and then that's where our H plus is, right? Here's our H plus, or our H plus. So those are our common acids, right? Again, pH less than 7 in the acidic range. And then now we have our bases. These are our Arrhenius theory bases. And I'm reviewing this because we're going to go into a different theory of bases, pH greater than 7. And here we have the OH minus as the only negative ion in solution. Okay, so why do we include ammonia here in this common level of common table L of bases? Well, that's what we're going to talk about in our next set of notes. So in our next set of notes, this is page 101 in your notebook. So get your notebook out and let's get ready to start. Okay, so we have this what's called the alternate acid-base in theory. And by alternate, it doesn't necessarily mean that the other theory is wrong. It just means that the other theory didn't explain all acids, all bases, all the time. And remember, in science, theory does not mean guess or judgment. Theory means it's been established through experimentation. So this is called the Bronsted, so Bronsted, Lowry theory, Lowry. Right, so we have two scientists, right, Bronsted and Lowry. And I like to call this the bad theory, and I'll explain that later. So this is our bad theory. Doesn't make it bad, but that's just going to be a little memory trick to help us. So then this explains weak acids and bases, because the strong acids and the strong bases have the H plus and the OH minus as the only positive ions in solution. So the Bronsted Lowry acid, so we have a definition for an acid, and then we have a definition for a base. We call the acids the proton. And remember, our proton is the H plus, right? We call those proton donors. And if something donates, it means it gives. So then we say then the acid donates the H plus. And donates to who? Or to what? To the base. Right? So acids are going to give away an H. So if an acid gives away an H, it's got to have extra hydrogen. So we know that this is HCl. And we know that HCl is an acid from our Arrhenius theory of acids. So if I look at this equation right here. So HCl in the presence of water, and now I have H3O and a Cl minus. So what happened from here to there? What happened from here to here? So let's examine this. So from there to there, we have HCl goes to Cl minus. So that basically means that this H left. It went somewhere. The law of conservation of mass says it has to have gone somewhere. So if I go from H2O to H3O. So it looks like I increased the amount of hydrogen over here. So then this is the acid. And if it's listed on table K, it's always going to be an acid no matter what, because it donated the H plus, right? It got rid of it. It lost it. If I donate something, I don't have it anymore, right? So it's going to be one less. So that is a Bronsted Lowry acid. So now let's talk about what is the opposite of an acid. The opposite of an acid is always a base. So here we have our Bronsted Lowry base. Oops, tricky. All right, so our Bronsted Lowry bases. So what's the opposite of a proton donor? A proton. Remember, proton is our H plus. And then acceptor. So if I accept something from you, you give it to me and I take it. So then you do not have it anymore. And now I have that piece. I have the proton if I am the base. I have gained a proton if I am the base. I have gained a hydrogen. So water here acts as a base because it went from 2 hydrogens to 3 hydrogens. So we say that bases accept the H plus, which is, again, the proton. So this theory of acids and bases doesn't go into like pluses and minuses. This theory of acids and bases is all about which ones donate and which ones are accepting the H plus. And this is really important in biological processes, because in biological processes, we often deal with weak acids and bases. So now let's circle our this is just BL, Bronsted Lowry acids and bases. So now this is why I called this the bad theory. Right? So BAAD, the bad theory, because bases accept and acids donate. I want you to take a peek at that, and I want you to see which one do you think is the acid and which one is the base. Okay, so let's go through and let's examine H2O. So now I have to figure out, where is the partner to water on the other side? Where is the partner to NH3 on the other side? Well, they have to be similar to each other, and they have to be different by only 1 hydrogen. So between H2O and OH, those are different. So those are going to be partners. And then NH3 and NH4 are partners. They only differ by 1 hydrogen. So those are going to be partners. We call them pairs. We call them conjugate pairs. And we're going to use brackets, just like I did, or lines, to connect one side of the reaction to the other side, and they merely differ by 1 hydrogen. Okay, so what does this whole bad theory mean? So this Bronsted Lowry theory means bad bases, and then we have accept the H plus. This is just a memory trick to remember which ones accept and which ones donate. And then acids donate the H plus. Right? An acid has to have extra hydrogen, right? Because that's still part of, it still works with the other Arrhenius theory. So now let's use brackets. So HCl has got to connect to something on the other side of the arrow. And it has to only differ by HCl by 1 hydrogen. So that's going to be the Cl minus. It only differs from hydrochloric acid, HCl, by 1 hydrogen. And H2O and H3O differ by 1 hydrogen. So now we have conjugate acid-base pairs. So I have an acid and a base on either side of the arrow. We have an acid plus a base. And now we have our arrow. And now on the other side, I'm also going to have an acid and a base. But instead of a pure acid, we call it a conjugate acid. And we'll do Ca for short. And we'll have a conjugate base. So the acid and the base. So here, HCl is an acid. First of all, it's listed on table L. So, I mean, it's got to be an acid. If it's an acid by the Arrhenius theory, it's an acid by the Bronsted Lowry theory. And so now we have water is going from H2O to H3O. So what's going on between 2 hydrogens to 3 hydrogens? This water is going up in hydrogen. So then if this water is going up in hydrogen, it means it's taking it. It's accepting it. And that bad theory, bases accept, acids donate. So that means this is the base, because from here to here, it's accepting the H plus. So far, okay? So if this is the acid, and from here, from HCl to Cl minus, this one is losing a hydrogen from here to here. So then this is donating the H plus. So the acid donates to the base, and now we have a conjugate acid-base pair on the other side. So if this is the base on this side, we're going to flip its identity on the other side. We're going to call this the conjugate acid, right? And this is also our hydronium, right? Which is our acid ion. So it still makes sense. And then now if this is our acid on the reactant side, its partner has to switch identity. So now this is a conjugate base. Because if I read in the reverse direction, this is going to accept a hydrogen and this one would donate in the reverse direction, right? Reverse is reading from the opposite direction. So those are what we call our conjugate acid-base pairs. So notice the acid always has one more H than the base. All right, so this just gets easier with practice. I know it's a little bit weird, especially a little bit weird trying to, try to get this from, this video. So we're going to use brackets, and we're going to figure out we have to have an acid and a base on either side of this arrow. So NH3, we got to find its partner, NH4. Remember, the partners differ by 1 hydrogen. And then HOH and OH differ by 1 hydrogen. So that's my first step. My second step is I need to figure out which ones donate and which ones accept the H+. Bases accept, acids donate the H+. So NH3, well, first of all, it's on table L. So if it's on table L and it's listed as a base on table L, it's going to be a base. But let's prove it. NH3 goes from NH3 to NH4. That means it goes up by 1 hydrogen. That means it has increased in hydrogen. So bases accept, right? If something is accepting, it's increasing in what it's owning, right? If I'm accepting an H+, I now am possession of 1 more H. So then this is our base. So then if this is the base on this side, it's partner, conjugate, acid, switch identity on the other side. So now I have HOH to OH minus. Well, if I identified this as the base, this has to be an acid, right? Because you have to have an acid and a base on both sides. But let's prove that that's an acid. Acids donate an H plus. So that means that from the left side to the right side, a hydrogen should be going away, which it does. So then this is our conjugate base because it was an acid on the other side. All right, so now let's go on to problem number 2. So first step, identify the partners and connect them with a bracket or a line, whatever you like. So HCl to Cl, right? Remember the partners are only different from each other by one hydrogen. HOH and H3O. I go from H2O to H3O. So now I'm going to look over on the left-hand side. I'm going to try to identify an acid or a base. Try to do it using reference table K and L if you can, right? So this is on table K. If it's listed on table K as an acid, you have every right to label that as an acid. So that is the acid. Its partner, switch identity, conjugate base. So if this is the acid, then this has to be the base. And so then its partner, switch identity, conjugate acid. All I did was draw brackets and I used my reference tables. Now let's prove it. Let's track the H and see where the H is going. So HCl goes to Cl minus. So that means that hydrogen has decreased. So bases accept, acids donate. So if I'm decreasing in hydrogen, that means I'm giving my hydrogens away. So I'm donating. So acid. HOH goes to H3O. So HOH is 2 hydrogens. This has 3. So if I suddenly go from 2 hydrogens to 3 hydrogens, I have acquired a hydrogen. That's a base. Bases accept. Okay? Let's try another one. All right. My suggestion would be for you to pause the video, and I would like you to try problem number 3. I would like you to see which one in problem number 3 is the acid. And then which one is the base. Okay, so problem number 3. So which one is the acid? Which one is the base? All right, so let's first step, connect with brackets. H to I, differ by 1 hydrogen. OH to H3O, differ by 1 hydrogen. Let's see, can I use my reference tables? Can I use table K? Let's take a peek at table K, why don't we? All right, table K. Well, I don't see HI. But if I remember from my set of notes before, anything hydrogen with group number 17 is going to be an acid. And iodine is a group 17 nonmetal, so then that would be hydroiodic acid. So I can use that and I can identify this as an acid. But let's prove it. Bases accept, acids donate. So if this is an acid, it should donate its hydrogen somewhere else. If it's donating its hydrogen, it's losing some hydrogen. So HI goes to I. Has it lost hydrogen from the left to the right? Yes. So that makes it an acid, right? Because it donates. So if this is the acid, that has to be the base, because there has to be an acid and a base on the reactant side. There has to be a conjugate acid and a conjugate base on the product side. So if HI is the acid, it switches identity with its partner, so conjugate base. And so now if this is the base, this is the conjugate acid, H3O, right? This is our hydronium ion, which we've identified as the acid ion. So that is your conjugate acid. So let's prove it. HOH is 2 hydrogens to 3 hydrogens. So that has increased the hydrogen. It has accepted one more. So that is a base because it is accepting. So that water is the base and its H3O is its conjugate acid. Okay, so now over here, let's take a look at, we have HNO3 to NO3, and we have H2O to H3O. So HNO3 is an acid because it's listed on table K as an acid. HNO3, nitric acid. There we go. Just use my reference table. If that's the acid, that's a base. Okay, so then now let's connect the partners. If HNO3 is my acid, its partner is the conjugate base, right? This flipping the identity. And then base, conjugate, acid. All right, so now let's prove that. HNO3, if it's an acid, bases accept, acids donate. So if HNO3 is in fact an acid, it should donate its hydrogen to something else. So if it's donating its hydrogen, it's going to lose the hydrogen and go to NO3. Does that work? Yes. Acid. So now if water over here is the base, that means it's going to accept a hydrogen. That means it's going to go from 2 to 3 hydrogens. Does that happen from here to here? Yes. So that is in fact the base. Notice how water has been able to do a couple of different things. Water can behave as either an acid or a base. And we call that amphoteric or amphiprotic. And that is basically a substance that can act as an acid or a base. Can it be either? So let's take a look at this weird equation over here. I have H2O, H2O forming H3O and OH minus. Okay, so I have to identify my conjugate acid-base partner pairs. So if I have water and it goes to H3O, I can have water and it can go to OH because water can increase in hydrogen to go to H3O, or it can decrease in hydrogen to go to OH minus, right? And so that means bad theory, bases accept, acids donate. Water can donate to go to the OH minus, or it can accept to go to H3O. So water is amphoteric or amphiprotic. Water acts as an acid and a base. Remember, water is neutral, pH 7, because it has an equal amount of H and OH. So amphoteric substances must have at least one hydrogen in their formula. And we're not going to work on identifying amphiprotic right now. We're going to skip that. Now let's talk about pH, the power of hydrogen. So we talked about the pH in our first set of notes, and now we're just going to go a little bit more in depth about what is pH. So pH is a measurement, and pH is actually a value, and it is the measurement of the, I'm just going to do this, pH is the minus log of the concentration of hydrogen ions, right? And so concentration is going to be equal to molarity, right? Which we did in our solutions unit, which is moles over liters. So if I know the molarity, I can figure out the pH. I can just stick that into a calculator, hit the log button, and hit the little minus button. There you go. Then you've got yourself the pH. So your pH scale goes from 0 to 14. And it is a measure of the H plus. It doesn't measure OH minus. It just measures H plus. And it's logarithmic. So that means that from 0 to 1 is going to be 10 times. 1 to 2 is a 10 time factor difference in acidity. And now if I go from a 1 to a 3, that's 100 times. If I go from 1 to 4, that's 1,000 times difference in molarity concentration. Right? So if I go from a pH of 1 to a pH of 2, you're like, yeah, 1 to 2, no big deal. Well, a pH from 1 to 2 is a big deal. Okay? So the pH scale, again, goes from 0 to 14, acidic to neutral to basic. So here's the diagram that we've had in our first set of notes. So notice as I go from 0 to 7 to 14, what's happening to these H's, right? H plus is decreasing. And then it's decreasing by factors of 10, right? Because it is a logarithmic function, right? So every pH value change is a factor of 10. All right, so now let's look at our OH. So from 1 to 14, our OH minus is increasing, but our H plus is decreasing. And then by what? By factors of 10. Oops, let me erase that here. Okay, by factors of 10. So in an acidic substance, you have H plus is greater than OH minus. But OH minus is less than H plus. Okay? In a basic substance, OH minus is greater than the H plus, right? Because that's what makes it basic. And then the reverse is also true. In our neutral substance, the concentration of H plus equals the concentration of OH minus. Logarithmic scale based on the number 10, base 10 logs. So pH is the minus log of the H plus. Don't worry, I am not making you calculate logs. All you would have to do anyway would be put the number in the calculator and hit the button. No big deal. So if I have a 1 molar solution and I put this into the calculator, the minus log of 1 is 0. Now if I have a 0.01 and I do this minus log in the calculator, this is 2. If I do the next one, 3. If I do the next one, 4. So then 2 places after the decimal place, 3 places after the decimal place, 4 places after the decimal place. Let's put 1 in scientific notation. This is 1 times 10 to the power 0. This is 1 times 10 to the minus 2. 1 times 10 to the minus 3. 1 times 10 to the minus 4. Do you notice something about the scientific notation and the pH values from here? Whatever your exponent is, that is your pH. So if I go from a pH of 2 to a pH of 3, this is going to be 10 times different because it's a logarithmic scale. This is 10 times less acidic, right? Because when pH increases, right, that means the acidity decreases. So now if I go from a 3 to a 4, this is 10 times less acidic than a pH of 3. A pH of 4 is 10 times less acidic or 10 times more basic. Even though a pH of 4 is still in the acid range, it is 10 times more basic because remember, when we take a look at our little diagram over here, there's H and OH present in every sample. So, oops, don't mean to do that big draw there. And let's just try to erase that. Okay, so now let's go back down here. So now every single pH unit signifies what we call a 10-fold, right, which just means multiples of 10 change in H plus concentration. So now let's look at some examples. So here we have our 0 to 14, right? We have our neutral, right, where we have H is equal to OH. We have our strongly acidic, which is our H plus is greater than our OH minus. And we have our strongly basic, which is our OH minus is greater than our H plus. So if I'm going to go from 4 to 5, so 4 to 5, I love number lines. Did I go to more basic or did I go less acidic? Well, I went from 4 to 5, so I moved to the right, which is towards the base side. So that is becoming more basic. So what's happening to the OH, right? So then if I draw my little wedge diagram here, right? So if I go from 0 to 14 and H and OH, right? So what is happening to our H and our OH? So our OH is going what? So if I'm going this direction, the OH wedge is getting bigger. So it's increasing by 4 to 5 is 1 hop. So every hop is a multiple of 10. So by a factor of 10. So then it is going to be more or less acidic. It's going to be less acidic. And the H plus is decreasing by a factor of 10 from 4 to 5, right? So from 4 to 5, it's getting more basic. H plus decreases, OH minus increases by a factor of 10 because I went from 4 to 5, which is just 1 hop. 1 multiple of 10 is 10. Okay, so now let's go from a pH of 13 to a 10. Okay, so 13 to a 10. So if I'm starting at 13 and I'm going to 10, 1, 2, 3. Okay, 3 hops. 3 pH value changes. So let's just freeze here. So then this is going to be a pH change of 3 hops. I'm just going to write 3 hops because I don't want you to think anything else. So every hop is a multiple of 10. What is 3 multiples of 10? So 3 times 10. 3 multiples of 10. Not 3 times 10, sorry. Let me erase. Okay, not 3 times 10. 3 multiples of 10. So I meant to write 10 times 10 times 10, which is what? 1,000. 3 hops, 3 zeros. So then this is by a factor of 1,000, right? If I change the pH value by 3, I have influenced the pH by a factor of 1,000. And if I'm going from a 13 to a 10, I'm going this way on my pH scale. So then I'm becoming more acidic. Even though a pH of 10 is still in the base range, it is 1,000 times more acidic than a pH of 13. So what is H plus doing? H plus is increasing because here's this thing, right? H, OH, right? So if I'm going in this direction, my wedge of H plus is increasing. So now let's look and see what's happening to the basicity from 13 to 10. It is becoming less basic, right? It is 1,000 times less basic because it's 3 multiples of 10. And our OH is decreasing because going this way, the OH range, the OH wedge is getting smaller by a factor of 1,000. So let's look at some common substances and where, they fall on this pH scale. So if I look at lemon juice and let's look at battery acid. Battery acid is somewhere like around a 1. And then there's lemon juice, which is around a 2. So if I'm going from like a 1 to a 2, you're like, yeah, no big deal. 1 to 2. Well, it is a big deal because you're certainly not going to drink battery acid because that's just going to burn your esophagus and cause all kinds of damage. But can you drink lemon juice? Sure, you've all had lemonade before, right? Because every pH value, right? Every pH value is multiples of 10. So if I go from a 4 to a 7, 4, 5, 6, 7, this is 1,000 times less acidic. Right, so vinegar is going to be 1,000 times more acidic than milk. Milk is 1,000 times less acidic than vinegar. It's 10,000, right? If I'm going from the lemon juice to milk, right? Lemon juice is 10,000 times more acidic than milk. Lemon juice is 10,000 times less basic than milk. All right, so every pH value is a multiple of 10. All right, so that's really what's the most important part over here. So then strong acids and bases, right? So then it has to do with ionization. So sodium splits into Na plus and OH minus. The hydroxide is the only negative ion in solution. So this is a base, right? So then this is an electrolyte because we have these mobile ions, right? And we're going to have, this is going to have a really high pH, greater than 7. And here we have our acid H plus and our Cl minus. All right, so in our next set of notes, we're going to talk about our acid-base indicators. We're going to do a little bit of math, but I'd like you to make sure that you practice the difference in pH. So let me give you one more example before we wrap up. If I'm going to give you a pH equal to, let's say, let's make up a number. My favorite number, well, let's go with a 7. So if I have a pond, I like ponds, they're pretty. And I have a pH of 7 in my pond because it's a very beautiful, pristine, clean pond. It's the best pond. It's the greatest pond there ever was. And oh my goodness, what happened? There's an acid spill into the pond. So somebody forgot something and they drove off the road. They were driving a truck full of acid. The acid spills into my beautiful, pristine, wonderful pond. And what happens is my pH is going to change by 100-fold. I want to know what is the new pH. Okay, so how do I figure this out? If I started at 7, so let's draw a number line, 7, and we'll do 14 and 0. Okay, so here's my acid and here's my base range. So here's where I start my pond here, and I spill acid. Is it going to go, which way is it going to go? Is the pH going to go up or is the pH going to go down? First, let's got to figure out that, right? It's either up or down. Well, this is our acid range, 0 to 7, and this is our base range, 7 to 14. If I'm spilling acid into something, it's going to become more acidic. So my pH is going to have to go down. So it's going to have to be less than 7. So then it's going to be less than 7. But how much less than 7? I want a number. It's 100-fold more acidic. Well, how many factors of 10 is 100? 2. 2 factors of 10. 2, and I'm just going to write that, 2 factors of 10. So 2 factors of 10 means the pH will change by 2. And it's going to go down. So it means it's going to go down by 2. So if I started at 7, it's going to go down by 2. My new pH will be 5. Okay, give yourself a check if you got that right, and make sure you answer the questions. And this will be it for this set of notes. Until our next time.